So we were looking at channel coding. Okay. So the goal was like there was this channel where the input of the channel is some random variable. The channel changes that random variable and it gives you something else. And based on the observation of what is at the output of the channel, the change random variable, you need to estimate what was sent. Okay. The question is, when a channel is imperfect, okay, how much information can you send? And we are saying like the channel coding theorem, which is like probably the most fundamental result or the first fundamental result. And it says that even though the channel is noisy, okay, if you are transmitting for a long time, and each time you are transmitting new information, it's not just you are transmitting the same information over and over again, okay. But if you are transmitting long enough, okay, even though you are transmitting new information every time, what you will find is that you can transmit this information reliably as long as the amount of information you are pushing through per channel use is less than a certain quantity. Okay, and it's a sharp threshold. If it is less than this quantity called the capacity, then you will have perfectly reliable communication asymptotically. But if you try to go even a little bit over the capacity, you'll have perfectly unreliable communication. Okay, so so we define this notion of capacity. So suppose there is a channel. The input to the channel is a random variable. The output to the channel is the changed version of the random variable. And the channel is nothing but a set of conditional probabilities. Okay. So the channel is very abstract. Okay. We are not more. So we just say, okay, given a particular input, the conditional probability of the output is something. So that's what a channel does. Okay. It's simply a set of conditional probabilities. Okay, so given any input, right, so the channel just tells you what's the probability of the output symbols. Okay, and we saw a couple of examples of this, right? And so we defined the capacity of this channel to be the maximum mutual information between, right? So the inputs of the channel are specified, but I mean the channel can only take certain inputs. Okay, but the distribution on these inputs is under our control. Okay, and the distribution on these inputs determines this random variable x. Okay, so that even though like a channel can be in, so like with the binary symmetric channel, right, it can only take input 0 or 1. Okay, while it can take only input 0 or 1, it is still under our power to say what is the probability of 0 and what's the probability of 1. Okay, so we can send in any Bernoulli random variable as an input. Okay, so x is the binary symmetric channel is x would be a Bernoulli tree random variable. The t is under our control. Okay, now if x is a random variable conditioned on each input, that is condition on x equals 0, there is a probability distribution on the output of the channel. Condition on x equals 1, there is a probability distribution on the outputs of the channel. Okay, so together, because we also have a probability distribution on x, it determines a new random variable y. Okay, and this new random variable y is dependent on x. Okay, it depends on what we transmitted. Okay, the amount of information that y says about x is the mutual information. Okay, now we want to maximize this over all possible choices of the random variable x. And this is the capacity of the channel, right? And we had a couple of examples. Right? So when we had the binary symmetric channel, the capacity was 1 minus the entropy of the crossover probability. Little h of epsilon is just this quantity. Okay, we also did the capacity of the erasure channel. Right, so for an erasure channel where the erasure probability is epsilon, okay, the capacity of the channel is 1 minus epsilon. Okay, so we computed both of these. Okay. Now, what it means is that this is the amount of information you can push through per channel use. Okay. So if you use the channel 100 times, you can send in 100 times 1 minus h of epsilon bits in the 100 times 1 minus h of epsilon bits. Okay, in 100 channel users. Okay, or if you use like a million channel users in the binary erasure channel, okay, with erasure probability epsilon, right? So then you have a million times 1 minus epsilon bits. That much information you can send through in this period, okay, in a million channel users. So that's kind of the story, okay, and the way we do it is kind of important, okay, because this is what we would call like a channel code, and it is fundamental to how, even though the channel keeps changing your bits, okay, the channel keeps changing your data, so you still get it across reliably, okay, and okay. So there is the notion of a channel code, which also we looked at, but we'll go over again because it was before the break. Okay. So the idea is like, okay, let us say that you want to transmit in n channel users. You want to use the channel n times. Okay. You're going to use the channel n times, and remember that these are discrete memoryless channels. Right? So like we mentioned before, when you're using the channel n different times, the channel acts on every, so each time in the ith step, if you have an input to the channel acts on the ith input independent of what has happened in the other bits, okay, in the other transmissions. So every time the channel retains no memory of what was sent in the past, okay, or what was received in the past. Okay, so every time the channel only looks at what bit is there and independently acts on it. Okay, so the purpose is to transmit in n channel users, and we in order to do that, okay, we will use something like something called a code. Okay, so first, like we need to determine like how much information do we want to send. Okay, let us say that we want to transmit r bits per channel use. Okay, right. So it's r bits per channel use, and therefore since there are n channel users and r bits per channel use, this means that we want to transmit nr bits totally. Okay, and all the channel users put together, you want to totally transmit nr bits. Okay, you're not going to transmit like r may be even a fraction. Okay, So it's when we say R bits per channel use, it doesn't mean that every single bit, like every single use, you want to push R bits. This is only on an average, okay, over n channel uses, which means that in n channel uses, you want to transmit NR bits totally, okay? And we have an abstract way of thinking about it. We assume that there is a message set M which contains numbers from 1 to 2 to the NR. Okay, this is a set with 2 to the NR elements. Okay, and our message is one of the numbers in this set. Okay, now the amount of if we choose these numbers uniformly, okay, the entropy of M or the amount of information that you get when you observe what number was chosen, okay, that is log of the size of this set, then log of 2 to the NR is NR bits. Okay, so if we have this abstraction where n is a set of size 2 to the NR, okay, we think of a random variable, let's say W. Okay, now W is a random variable, it's uniformly distributed over the message set. Okay, observing the value of W gives you NR bits of information. Okay, does that make sense? Right, so if it's not 100% clear or you're wondering why we are getting all these numbers, you need to ask. Okay, they're not uh, they're not something that we should ignore. Okay, so is this clear? Right, so the entropy of W is NR bits. Okay, therefore observing W, okay, gives you NR bits of information. Okay, and so here is what we do. We transmit this, we are going to transmit this W over the channel. Okay, now W is a number from 1 to 2 to the NR. Okay, and if you want to transmit it over the binary symmetric channel, okay, how are you going to do it? With the binary symmetric channel, for example, only allows inputs of 0 or 1. Okay, the input to the channel can only be 0 or 1. Okay, it can't be any number. Okay, so how would you try to transmit W over the channel? Right, so you would want to encode it. So you want to translate these numbers 1 to 2 to the NR with like a sequence of bits. Okay, and you're potentially going to transmit this sequence of bits over the channel. Okay, now you don't want, so if you just use like a binary representation of these numbers, okay, there's no guarantee what is going to happen. Okay, some of the bits may get corrupted and then you don't know what to do. Okay, so you also don't want to just repeat bits. That's wasteful. Maybe there are smarter ways of doing it. Okay, so what we have is like an abstract code. Okay, so but because regardless of what you do, you're going to do something like this. You will have you'll have a table. Okay, and in this table, the first column is the message. Okay, the message can be any number from 1 to 2 to the NR. Okay, corresponding to every message, you will have a sequence of bits, that is the encoding of that number that you are actually going to transmit. Okay, so you're going to use you're allowed to use n channel uses. Okay, so which means like you can encode one with a message as long as n bits. Okay, uh, with as long as n bits. Okay, so I'll call these bits x1, x2 through xn. Okay, so these are the bits that we use to transmit, to indicate that the message is 1. Okay, And because we need to keep that, I'll just say x1, x2, xn of 1. Okay, this is called the code word for 1. Okay, you do the same thing for 2. Okay, so this is a potentially different sequence of n bits. Okay, and you transmit the bits in the second row. Okay, if your input is 2. Okay, and so on. So every input okay. So no matter what the input message is, okay, so you translate it into a sequence of bits which you're going to transmit. Okay, so x2 of 2 to the n is it's a bit, it's the second bit, it's the bit you would use as the input in the second use of the channel when your message is 2 to the n. Okay, so does that make sense? Okay, now this table, this entire table, is the code. Okay, as far as we are concerned, this is like a table where it has 2 to the n rows and n columns. Okay, so it has n times 2, so it's like a matrix of size 2 to the n times n. Okay, n columns and 2 to the n rows, and each entry of this matrix is 1 bit. Okay, it's either 0 or 1. Okay, and this is going to be our code. Okay, now there are different possible codes. Okay, how many different codes are there? So every matrix of this size is a code. Some are good codes, some are not good codes. Okay, we don't care which ones are good, which ones are bad, but how many different codes are possible? Right. Okay. So, right. So, generally speaking, like, so for the binary symmetric channel, okay, so every entry is a bit. Okay. So if the alphabet, so if each entry if the input to the channel is binary, that means that each of these entries has to be a bit. Okay, there are 2 to the nr times n. Codes. So there are these many codes. Okay, because every entry of the matrix you can either pick 0 or 1. Okay, and there are n times 2 to the nr positions, and for each position you can either have a 0 or a 1. Okay, so all in all you have 2 to the n times 2 to the nr codes. Okay, so there are these many different codes. Okay, so does that make sense? Okay, now here is what we are going to do. We need to show, so the channel coding theorem says that there is some code. Okay, it doesn't tell us which code, what the code is. Okay, but it says that there is some code. Okay, which will achieve as long as R is less than the channel capacity. Okay, there is some code that will achieve as small a probability error as you want, provided n is large. Okay. Okay. Or equivalently, so here, by probability of error, there are multiple ways things we could mean. I mean, there are multiple metrics that we discussed before. Okay. This could be the average probability of error. Okay, what would be the average probability of error? Now look at this code. Okay, now let us say that you pick the message uniformly. Okay, the message can be 1 to 2 to the nr uniformly. Okay, so you should pick any one row. Okay, uniformly among all rows, and you transmit the code word corresponding to that row. Okay, now the channel corrupts that code word. Okay, and you receive like a sequence of bits at the output. Okay, now pick the smartest decoder. Okay, the best possible decoder that you have. Okay, now what is your decoder? A decoder is anything that looks at the channel output and figures out what the message was. Okay, now pick the best possible decoder you have. Okay, the best possible decoder you could come up with. Okay, now even this decoder will make errors sometimes. Okay, when it confuses the message sent in one row with potentially something else in some other row. Okay, that is because like you never get the message correctly. Okay, you always have errors that are incorporated. So there's always a chance that the decoder can look at this and think that some other message was sent. Okay, now this is the probability of error corresponding to the conditional probability of error given this particular message. Okay, now you can either average it over all messages or you can take the maximum over all messages. Okay, and when we say this probability of error, whether you're looking at the average or whether you're looking at the maximum, okay, this theorem holds. Okay, so you could, for example, write it as two theorems. You could say if r is less than c for any epsilon there is n and therefore such that the average probability of error is less than epsilon. Okay, or you could have a slightly stronger version of the theorem that says if r is less than c for any epsilon there is some code such that the maximum probability of error condition on any message is less than epsilon. Okay, so the maximum probability of error is less than epsilon means that no matter what message you send, okay, the probability that it will get mistaken for something else is at most epsilon. Okay, average means for some messages they probably get corrupted much more. Okay, in some messages less, but on an average your probability of error is less than epsilon. So does that make sense? So the average probability of error is therefore the. So let's just set some notation. So we had this random variable w. Okay, now w was translated with this code to the code word. Okay, so from w, okay, we got this code word. Okay, so this is just the w row of the matrix. Okay, now this goes through the discrete memoryless channel. Now again, the discrete memoryless channel means that the channel acts on each of these xi independently of what has happened to the other symbols. Okay. and you get y1 through yn, okay? And your decoder looks at y1 through yn. Your decoder can only look at y1 through yn. It doesn't know anything about what happened in the channel, okay? It may know the statistics of the channel. So it may know that you have a binary symmetric channel with transition probability epsilon, okay? But it doesn't know what has happened to any of the individual bits, and obviously doesn't know what x1 rates are, okay? And it also doesn't know what W is, but it wants to figure out the best guess of W from y1 to yn, okay? So it outputs its guess, which is W hat, okay? So the probability of error or the average probability of error here is the probability W is not equal to W. Okay? So this is the average probability of error, okay? And when you think of it, this is the probability W is not equal to W hat, given that W equals I, okay? Right? So this is the probability W is not equal to W hat is an average, okay, of the conditional probability of error given W equals I, okay, averaged over all possible messages, okay. So this is the average probability of error, okay. You can also have the maximum probability of error, right, instead of averaging this out over all possible values of W, taking an expectation of this, you can think of this as like a random variable that depends on the value of W. Instead of taking an expectation like here, you want to take the maximum value of the random variable. Okay, so this is the maximum probability of error. Okay, now either one of them drops to 0. Okay, so as you are looking at larger and larger codes, and if you want to transmit over longer windows, but also send more information, okay, whether you're looking at probably average or the max probability of error, they'll all drop to 0. Okay, and that is the channel coding here. Okay, so is this clear, like what we are talking about? Okay, it's particularly important to note that n being large, so we have said it several times, okay, but n being large, it's not like, okay, over a binary erasure, over a binary symmetric channel, right, you transmit a 1 or 0, sometimes they get wrong, okay, but let us say that you transmit it like many times, okay, you transmit a single bit like hundreds of times, okay, now and you take the majority at the output, okay, now chances, the probability that as the number of transmissions increase, the probability that the majority doesn't agree with what you sent, okay, goes to 0 if epsilon is less than 1/2, okay, so clearly, like here, you transmitted one bit reliably, okay, but this is not what the channel coding theorem is telling you, okay, it's telling you something much stronger. In this case, the even though you transmitted this bit reliably, okay, your rate is 0, okay, because the number of bits you sent was only 1, but the number of channel users became very large. Okay, so your rate is only 1 over some large number, And so the larger the number of channel users, the more reliable it is, but also your rate is zero. Okay, so this is not the interesting situation. Okay, the interesting situation is that somehow you're transmitting new information every single channel use, okay, and still getting away with perfectly reliable communication. Okay, right. So, and we said, like, for the proof of the channel coding theorem, we need this notion of joint typicality. Right, so it's a little stronger than typical sequences that we described, but it's a more powerful one. Like here, you have two random variables x1 through x and y, okay, and we say a sequence of, so you can think of this as an ordered pair of random variables, okay. Now, let us say you get a lot of them, x1, y1, x2, y2, so on. Okay, now think of this as the input-output of the channel for each of the n-channel users. Okay, and we say these are jointly typical. Okay. Okay, so these ordered pairs are jointly typical if the following things happen. Okay, one, x1 through xn is typical. Okay, which means that the probability of x1 through xn, just the marginal probability of x1 through xn is less than 2 to the minus n h. Okay, so let me just pause a little bit. Okay, so we take this ordered trait. Okay, and we are generating x1, x2, x1 by 1, x2 by 2, and so on. Okay, now for the moment, okay, imagine that this is IIT. Okay, now there is something that should bother you at this point. Okay, because in a channel code, right, the operation, so here it's important to note the distinction. How does the channel code work? Okay, the channel code is a matrix that we choose. Okay, and we definitely do not want to, when you're looking at the code word, right, like we want to choose the code word smartly so that they cannot get confused with each other. Okay, and typically what will happen is that the code symbols that we choose, okay, when you look at x1 and x2, okay, so if you're looking at the distribution of how are so the code symbols, okay, you pick a message, you pick a row at random, okay, that's your message, that's how you pick a message at random, you choose the entry corresponding to that row, that is your x1. Okay, now you pick an entry at, you pick for x2, it's the second column for that same row. Okay, and so on. Okay, so that is the mode in which you generate this x1, x2 to xn. Okay, now when you think about it, there's no reason that this needs to be independent. Okay, when you fix a particular code, once you have chosen a particular code, okay, it's only if you have designed the code so that this look independent, like only for very specific constructions of the code will these appear to be independent. Okay, and even there, like it's not that they will all be independent. Okay, so if you so next semester there's a course on coding and cryptography, and we will look at like codes, for example, where so these are called Reed-Solomon codes. Okay, where if you look at x1, if you look at pairs of them, they will appear independent. If you look at triplets of them, they'll appear independent, but only to a certain extent. If you look at more than 10 of them, for example, at some point the independence breaks down. Okay, because the code we design with some structure. Okay, it is not meant to be like arbitrary. Okay, the code is usually designed very smartly. Okay, and so x1 to xn, like the way you think of it is that there is some redundancy among them because we know some of them will get destroyed by the channel. Okay, the channel will correct x1 through xn. Okay, and as a consequence, like uh, each of uh, each of them need to tell something about the other. They all need to carry some information about the other. That's the only way you can correct the errors. Okay, if for example the channel looked at x1, I mean corrected x1, no, none of x2 to xn carried any information about x1. Okay, channel messed this up. Okay, because nobody else says anything about x1, that information is lost. Okay, that cannot happen. Okay, so by necessity, like a good code, there will be dependence. Okay, there will be some dependence on random variables, on all these random variables. They have to tell you something about the other. Okay, only when they can tell you something about the other will it happen that you can erase some of them or you can destroy some of them, but still the others can fix what happened. Okay, so generally speaking, this x1 through xn, they're not IID, they're not independent. Okay, but we are actually going to use this joint typicality not in a very specific way. Okay, so for the moment, assume that x1 through xn are here, this ordered trace, these are chosen independently. Okay, now the interpretation here is that this x1, x2, xn, like while it may appear to be conflicting with our intuition that the code word symbols cannot be independent, okay, they're not going to play the same role. Okay, so that's why like we have this definition. Okay, so but imagine they were chosen independently. Okay, then we say they're jointly independent if x1 through xn are typical. Okay, so here they're chosen in this particular little example. Okay, maybe I'll say x tilde. Let me just use x tilde, okay, because it has the x's here have a different interpretation from the transmitted code word. Okay, they actually have the interpretation of like a conflicting code word, not a transmitted code word. Okay, so here x tilde and y, they are sampled IID. So x tilde 1 to x tilde n, they are IID. Okay, now x tilde 1 to x tilde n, they are IID, which means that looking at this alone, okay, x tilde 1 to x tilde n must be typical according to our usual definition. Okay, that means that the probability of x tilde 1 to x tilde n okay, then y1 through yn in exactly the same way must also be typical. Okay, and uh, it's not just that these two should be typical by themselves. Okay, they've joined this one. Okay, so if I look at this ordered pair as a random variable, okay, not just one component of the ordered pair, but I look at the entire ordered pair as a random variable. Okay, they should still be typical. Okay, does that make sense? Right. So one of the things to notice, like how important is the third one. Okay. So if I pick a typical x, okay. If I pick just x typical and just y typical, okay, what is the chance, okay, that x and y will both be typical? Okay, so it's like, right? So if so there is a marginal distribution on x. Okay, there's a marginal distribution on y. Okay, I pick a sequence, a lengthened sequence of just x's, a lengthened sequence of just y's. Okay, just from the marginal distributions. Okay, so for example, let us say, let's think of this channel like okay, so the crossover probability for this binary symmetric channel is 1/4. Let's say that the input distribution is a Bernoulli 1/2 random variable. Okay, so what is the output distribution? What's the probability x is 0 and y is 0?
It's actually
It's the probability
1/2 times 3/4.
Yeah, so probability x is 0 is 1/2. Okay, times the probability of 0 given 0 is 1/3. Okay, so this is 1/2 times 3/4, which is 3/8. What's the probability 0, 1?
1/8.
1 over 8. 1, 0.
It's the same actually. 1/8. Yeah.
1, 1 is 3/8. Okay, so this is the
3/8.
joint distribution. Okay, so this is the joint distribution. Okay, it means that you can see both x and y as 0 with probability 3/8. Okay, now what is the marginal distribution on y? What's the probability y equals 0?
It's 1/2.
Right, so it's 1/2. And what's the probability y equals 1? So 1/2.
Yeah.
Okay. So x is a Bernoulli 1/2 random variable. Y is also a Bernoulli 1/2 random variable. They're not independent. Okay, they are obviously dependent because y is the output of the channel when x was transmitted. Okay, so as a consequence, okay, x and y have a joint distribution. They're not independent. Okay, but both of them individually are Bernoulli 1/2 random variables. Okay, does this make sense? Okay, so now here is the question we asked. Okay, I know x is Bernoulli 1/2. Okay, since x is Bernoulli 1/2, I take a lengthened typical sequence, Bernoulli 1/2 corresponding to x. And we saw that Bernoulli 1/2 is a very peculiar distribution. In this particular case, all sequences are typical. Okay, when you're looking at a Bernoulli 1/2 variable, okay, going by this definition, all sequences are typical. Okay, so any sequence of lengthened input bits, they are typical. Okay, for x. Y is also Bernoulli 1/2. Okay, so if I'm just looking at y, okay, any lengthened sequence, binary sequence for y is also typical. Okay, now the question is, how many of them are jointly typical? Okay, because any lengthened sequence in x is typical according to this x typical. Any lengthened y sequence is y typical. So the first two are kind of automatically satisfied for every pair of sequence, for every x and y sequence. Okay. how many of those sequences will also satisfy the third one? Okay, so this is the question we are trying to ask. Okay, does that make sense? Okay, so because if we just had the first two, right, any lengthened sequence, any lengthened bits for x and any lengthened bits for y, they would satisfy the first two. Okay, the question is how many will satisfy the third one as well. Okay, and this is the question we ask right now. This is kind of one of the important course in the channel coding theorem. Okay, I need a different. The difference symbol. We already use tilde. The plain is for the code word, the tilde is for the this one, like any other thing that we can do on X. As I can. Okay, so x1 through xn, they're distributed IID according to the distribution on X data. Okay, so which means in this case, there were only one half random variables. Okay, okay. The second one is kind of important. So y1 through yn is distributed independently according to probability of y. So in our little example, y1 through yn are distributed IID Bernoulli one half. Okay, but here for this lemma, these y1 through yn, they're not chosen as the outputs that correspond to x1 hat to xn hat. Okay, they're different. These y1 through yn are distributed independent of x hat. Okay, so it's something like this. Let's say that I have a sequence x1 through xn. Okay, so I have x1 hat to xn hat. Okay, and Nick has a channel to me. Okay, so I send x1 hat to xn hat through this binary symmetric channel. Okay, Nick gets like a sequence of Y's. Okay, but Quinn does not see my x1 hat to xn hat. Okay, he only knows that Y's will be Bernoulli one half. Okay, so just for the sake of mischief, for example, let's say that Quinn chooses n bits according to the distribution of Y's. Okay, he knows it's Bernoulli one half, so he chooses a length n IID Bernoulli one half sequence. Okay, now, so the sequence x1 hat to xn hat that I have, okay, and the sequence that Nick has, okay, they were generated together, okay, and with high probability this will be jointly typical, okay, but the question we are asking is what is the probability Quinn's sequence will be typical with mine? Okay, Quinn did not come through this process of generating y from x at all. Okay, he just looked at the marginal distribution of y, randomly chose a sequence. Okay, what's the probability that Quinn's sequence will also be typical with mine? Okay, so so the lemma says that the probability that twin sequence will be jointly typical with 9, okay, is less than 2 to the minus n times the mutual information between x and y plus small other term. Okay. Right, following our notation, like we'll call this okay. The set of all sequences that are typical, that are jointly typical, we call A epsilon n, like usually that will also indicate xy to denote that these are the random variables we are thinking about. Okay. Right, so this means that, or equivalently, the probability x1 hat y1 xn hat yn belong to A and the proof of it is actually very simple. It's more understanding the statement of this problem that is crucial. Okay. Now, how do we do the proof? We know that x1 through xn is very likely going to be typical. Okay. So we want x1 through xn to be typical, and that we know. Okay. With high probability, x1 through xn will be typical. Okay. We also know that with high probability, y1 through yn will be typical. Okay. Now the question is, what is the probability that they are jointly typical? Okay. And the way we do this is very simple. Like so, we are just going to look at the probability, this particular probability. Okay. The probability that all these order A's will belong to this. Okay, so basically we look at this set A and epsilon xy. Okay, so the joint typical set, we look at all sequences there. Okay, and we just look at the probability of all the sequences when we are generating x1 through xn and y1 through yn according to this model. Okay, so for example, take any sequence. So I'm taking one particular sequence, x1, y1, right? So I take any one sequence, okay, within this jointly typical set, okay? Now this sequence in this jointly typical set, okay, from our definition, we know that x1 through xn is typical according to x, y1 through yn is typical according to y, and together they're jointly typical. Okay, so from the definition of the joint typicality, we know that. So if I take any single sequence in the jointly typical set and I look at just the x component of this sequence, okay, we know that the probability of that x component should satisfy this by definition. Okay, we also know that the y component of this, okay, and I'm using small letters here just in case it's not clear. Using small letters to make sure that this is not a random variable. I'm looking at one particular sequence in this jointly typical set. Okay, and we know that from the definition of the joint typical set, this should be true. Okay, so these two should be true from the definition of the joint typical set. Okay. Now, what is the size of the joint typical set?
It's 2 with power
Sequences can be there.
2 with power nh.
H what? Okay, so here this is the number of sequences is 2 to the n h of xy plus epsilon. So this can be the total number of sequences in the joint typical set. Okay, why is that? Right? This is because the probability of the jointly typical set, the probability of any set is less than 1. Okay, the probability of any set is less than 1, including the probability of the jointly typical set. Okay, and what's the probability of the jointly typical set? This is all sequences within the jointly typical set. Okay, the probability of this sequence. Okay, so the probability of a set is like this is a set of sequences. The probability of the set is the probability. It's the probability of each individual sequence in the set added up, right? So if the jointly typical set contains like 10 sequences, okay, each sequence has a particular probability. The probability of this set is the probability of these individual sequences added up. Okay, does that make sense? Okay, but from the definition of joint typicality, right? So each of these sequences has probability at least, right? Each sequence must have probability at least 2 to the minus n x y plus epsilon. So that's the third. That's what we are saying here. Okay, in the jointly typical set, each of these sequences has probability at least 2 to the minus n x y plus epsilon. Okay, there can't be two small probabilities. Okay, and that is, and this summation is now, so this term does not depend upon this sequence. Okay, so this, I can take this term out. And this is simply 2 to the minus n. Okay. So I add 1 for every sequence in this set. Okay, so this summation is simply the size of the set. Okay, for every sequence in this set, I include a term of 1. So all I'm doing is counting the size of that set. Okay, so but when I look at the first and last, this one, if I look at this, so this implies that the size of the typical set is less than 2 to the minus n h. So the size of the jointly typical set is less than 2 to the n h of the joint entropy plus epsilon. Okay, so this is the size of the jointly typical set. Okay, now going back, okay, if I look at sequences in this typical set, okay, every x sequence has this probability, every Y sequence satisfies this because they are typical. Okay. I also know that the total number of sequences in the jointly typical set is this. Okay. And in fact, like this is all we need to figure out this lemma. Okay. Because according to this lemma, we are choosing x1 hat to xn hat independently from y1 to yn. Okay, so in this weird model, okay, so remember I have x hat, okay, Quinn has the y that is associated with my x hat, okay, that are jointly observed with x hat, okay. Quinn on the other hand has a y which is completely independently generated from x hat, okay. But if I'm looking at any sequence, so what is the probability my sequence and Quinn's sequence together are in the jointly typical set, okay. So the fact remains my sequence satisfies this probability because it's typical. Twin sequence independently satisfies this, okay, because he chose a typical sequence. Okay. Now, what's the probability that when we had an independent model of generating x hat and y hat, what's the probability that together our sequence is typical? It's the probability that we observe one of the sequences in this typical set. Okay. Now, so it's the probability that we observe one of these 2 to the n hy sequences. Okay. Right, so just a second. Okay. Right, so right, so in our new model, x hat and y hat independent. X hat and y are generated independently. So the probability so the probability that we generate this particular sequence x hat and this particular sequence yn, okay, this is simply the product of x1 hat to xn times probability y1 to yn. Okay, it's simply the product of these probabilities. Okay, and this is less than 2 to the minus n right? Because we generated x hat and y independent, the probability we get this particular sequence in the typical set, okay, is the product of these 2 probabilities, which is just 2 to the minus n x hat, 2 to the minus this one. Okay, so this is one sequence in the typical set. Okay, so the probability of the entire typical set, entire jointly typical set, okay, now these are random variables, these are not one particular sequence. Okay, so this is a random variable, this is meant to be like one particular sequence. right? So the probability that the random variables we generate belong to the jointly typical set is simply the probability of each of the sequences in the jointly typical set generated according to our model. But according to our model, each of these sequences in the typical sets have probability at most 2 to the minus n h of x. Okay. Right. So every sequence has probability at most this according to our model. Right. And the number of sequences in the typical set is less than hxy plus epsilon. Okay. What is h of xy? What is h? So the mutual information, for example, uh, what's the mutual information between x and y? Any one definition? Not joint entropy. So the mutual information, so think of it this way, it's the amount of information y gives about x. Okay. Now, how much information is there in x? It's h of x. Okay. This is what you would get when you saw x by itself. This is the amount of information you would acquire. The amount of
Minus.
information you acquire when you observe x after you see y is h of x given y. Okay, the difference between the two must be the information y told you about x. Okay. Also, the joint entropy h of xy. If to describe x and y, you need to first describe x. Okay, so or you need to first describe y, and then you can describe x given y. Okay. Now put these two together. Let's substitute for h of xy from the second equation and put it into the first. What do you get? Okay. H of x given y is h of x1 minus h of 1. Okay, use that in the mutual information equation. So what do you get? So hx plus hy minus h of xy. Okay, so it's something like if you observe x by itself, like you get this. If you observe y by itself, you get h of y by x. If you observe them together, you get h of xy. The difference must be the information y already told about x or x told about y. Okay, so but in particular, this means that we can simplify this to 2 to the minus n. Okay, so h of this and h of x plus h of y minus h of x. Okay, does that make sense? Okay, the proof of the channel coding theorem, it requires like two very spectacular ideas, which are both conceptually very, so they're very elegant ideas. Okay, so we'll take up the proof of the channel coding theorem next class. Okay, sorry, it went a little slower because I realized like Every time there is a break, we kind of need to repeat the class before the break. Okay, so we'll continue on Wednesday. So any questions? Right? So this means that in this example, right? So in this example, the what is the what is happening here, right? So here, like if you take any, so here all X sequences, all Y sequences, they're all typical. Okay, because they're both Bernoulli 1/2, every sequence is typical. Okay, now, but so there are 2 to the n sequences here and 2 to the n sequences here that are typical. Okay, the all combinations of these sequences is 2 to the 2n sequences. Okay, so there are 2 to the 2n combinations of sequences, but the number of jointly typical sequences between X and Y is actually far smaller. Okay, and that's why like every pair of sequences will not be typical. In fact, the probability, so we can compute the mutual information here, but whatever the mutual information here is, let us say this I, okay, the probability that, so among all these 2 to the 2n sequences, okay, only about 2 to the minus n times I sequences, so 2 to the 2n minus 2 to the n times I, okay, so those many sequences will be jointly typical. Okay, so I'm not sure what the mutual information here is, like, but we can compute it numerically maybe next class. Okay. Okay, so does that make sense? Okay. So we stop here. We'll continue next class.
Thank you.